Now we will obtain an exact solution for the problem of torsion of elliptical prismatic bars using Saint Venant's methods. So our problem is to obtain a obtain a warping function psi which satisfies the equation del square psi is equal to 0 and the boundary condition, that is dou psi by dou x minus y into dy by ds plus minus dou psi by dou y plus x into dx by ds equal to 0. Here we take a warping function psi is equal to axy, and here from that we will get dou psi by dou x is equal to ay and dou psi by dou y is equal to ax. If we substitute these values in this boundary condition, we will get the equations for the boundary as a y minus y dy by ds minus ax plus x dx by ds equal to 0. And if you multiply this by minus 2, what we will get? We will get negative terms. We will get 1 plus a into x 2x into dx by ds plus here negative of a minus 1 is 1 minus a into 2y into dy by ds equal to 0, and we can write this as d by ds of 1 plus a into 2x x square plus 1 minus a into y square is equal to 0. If we integrate this with respect to s, we will get 1 plus a into ax square plus 1 minus a into y square equal to a constant. This equation can be written in the form x square by a square plus y square by b square is equal to 1. These two equations are identical if a square by b square is equal to 1 minus a divided by 1 plus a, and from this we can get a is equal to by solving this we will get a is equal to b square minus a square divided by b square plus a square, and so the function warping function psi will become psi is equal to axy. Instead of a, here we have b square minus a square divided by b square plus a square into xy. Now we will come back to the boundary condition, that is now we have written in the form x square by a square plus y square by b square is equal to 1, which represents the equation of an ellipse having major and minor axes major and minor axis 2a, and this is 2a and this is 2b. So the boundary is an ellipse, so it represents the warping function corresponding to an elliptical cross section. Okay. Now as in the previous case, here we are going to find out the shear stresses. We know that shear stresses tau xy, tau xz is equal to, we know that shear stress tau xy is equal to 0, sigma x, sigma y, sigma z, all normal stresses are 0, and we have only two non-vanishing shear stresses, that is tau xz is equal to g theta into dou psi by dou x y, and here we also have tau yz is equal to g theta into dou psi by dou y minus plus x. Here we have dou psi by dou x is equal to, we have written here dou psi by dou x is ay and dou psi by dou y is ax. So the equation will become tau xz is equal to g theta into a y minus y, or g theta into a minus 1 into y, and similarly tau yz will become g theta into a plus 1 into x. So here if we take any area, any point p of xy in the ellipse, in this area, the area of cross section, here we have the values of shear stress tau xz is equal to g theta into a minus 1 into y, which is directed in this direction, and tau yz is equal to g theta into a plus 1 x, which is directed in y direction. So if we take a small area, elemental area dA here, the moment due to the moment produced due to these shear stresses about this point, which is the center of twist, we will get dm is equal to the moment due to this, this is the stress tau xz, we will get the force here, since this area is dou dA, we will get the force in this x direction tau xz into dA. So and this is the line of action is at a distance y from the origin, the center of the twist. So that is, and it will produce a clockwise moment, so we will put it as a negative value. So it is minus tau xz into dA into y, and due to this force, stress, there will be force will be tau yz into dA. Due to this force, the moment will be tau yz into this distance is x, and that will be in anti-clockwise direction. So that is positive. So tau yz into dA into x. Okay. So to obtain the moment due to all the shear stresses in the whole area, we have to integrate over the area. But we know that to maintain equilibrium, that should be equal to the torque applied on the end faces. So we can write T is equal to integral over area minus, we can take dA out, minus y into tau xz plus x into tau yz dA. Here we have equations for tau xz and tau y. We have calculated equations for tau xz and tau yz. Tau xz is g theta into a minus 1 y, and tau yz is g theta into a minus 1 x, a plus 1 x. So T can be written as integral over a, here minus y into tau z is a minus we can write y into a minus 1 plus x into tau yz is given by g theta into a minus 1 into y. Oh sorry, g theta term is there. Okay, that we will take, and here also we can write into x into a plus 1, and we can take we have common g theta term, so we can write g theta here and g into dA. Since g theta is constant, we can take this outside of integral, and it can be a into, we can write this as integral y square into a 1 minus a plus x square into one plus a into dA. So we can write this as t is equal to g theta into 1 minus a into integral or a integral y square dA plus 1 plus a into g theta, sorry, g theta is constant, 1 plus a into integral over a x square dA, and we know that this represents integral y square dA represents Ix is equal to integral y square dA, and that we have studied in engineering mechanics. Iy is equal to integral x square dA. Okay, if we put this in the equation, what we will get? We will get t is equal to g theta into 1 minus a into I x plus 1 plus a into Iy. This represents the equation which relates torque and the angle of twist in the case of an elliptical cross section. So we can write this as in the form t is equal to g theta into j, where j is equal to 1 minus a into Ix plus 1 plus a into Iy. Here substituting the values of 1 plus Ix and Iy here, we will get, we have in the case of an ellipse like this, where the 2a is major axis and 2a is minor axis, which is represented by the equation x square by a square plus y square by b square is equal to 1. X can be written as Ix is pi a b cube divided by 4. Note that x axis is along the major axis and y axis is along the minor axis, then only Iy is equal to pi a cube b divided by 4, and here we substitute these values, and we have a is, the values of a is we have calculated here, that is here, that is b square minus a square divided by b square plus a square. So we substitute these values in this equation. What we will get? We will get j is equal to pi, you can do it yourself, pi a cube b cube divided by a square plus b square. So we can write the equation for torque, t is equal to g theta into j, where j is this. So we can write this as t is equal to pi a cube b cube divided by a square plus b square into g theta, or the angle of twist per unit length can be calculated using by rearranging the terms. We will get angle of twist per unit length. Theta is equal to T by G into a square plus b square divided by pi a cube b cube, and that is the angle of twist per unit length, and this can be written like this. And we will have another term, that is we call as torsional rigidity, which is a measure of the stiffness of the bar under torsion, and it is given by G J, and we know that torque is given by T is equal to G J theta, and from that we will get torsion rigidity can be written as T by theta, and from the above equation we can write torsional rigidity as T by theta can be written as G into pi a cube b cube divided by a square plus b square.
This will give this. Now we are going to find out the shear stresses. We have already written the equations for shear stresses as tau zx is equal to g theta into a minus 1 into y, and tau yz is equal to g theta into a plus 1 into y. Okay. Now we know the values of theta and a. The value g theta can be obtained from here, that is t into a square plus b square divided by pi a cube b cube, and a is given as b square minus a square divided by b square plus a square. So substitute these values in the term z tau zx, we will get t into a square plus b square divided by pi a cube b cube into a minus 1 can be written as b square by minus a square divided by b square plus a square minus b square plus a square divided by b square plus a square. One can be written like this, and into y. So reducing this, we will get the equation tau zx is equal to minus 2t into y divided by pi a cube a b cube, and similarly if we substitute the values of a and g theta, we will get tau yz is equal to 2tx divided by pi a cube b. So these stresses, these shear stresses represents to find out the stresses at any point, so to find out the stresses at any point at any cross section, and the coordinates of that point is given in terms of x and y, and the origin is set at the center of twist, and x-axis and y-axis are the x-axis is along major axis which is having a length 2a, and y-axis along is along minor axis, and minor axis having length 2b. So we will get tau zx and tau yz like this. To find out the total stress at any point xy, we know that tau is equal to tau xz or zx, xz square plus tau yz square. So, and substituting the values of tau xz square and tau yz square, we will get tau is equal to 2t divided by pi a cube b cube into root of b raised to 4 x square plus a raised to 4 y square. And it can be shown that the maximum shear stress will be at the two extreme ends of the minor axis, that is y is equal to plus or minus b, and x is equal to 0. Along minor axis it will be x is equal to 0, and it will be the value of maximum shear stress will be substituting these values in this equation, we will get tau max is equal to plus or minus 2t divided by pi a b square. And similarly, minimum shear stress will be at y is equal to 0 and x is equal to plus or minus a, which means two extremes ends of the major axis, and tau minimum shear stress can be written as tau minimum is equal to plus or minus 2t divided by pi a square b. Now, we will look into the distortion of the cross section, elliptical cross section, because of twisting, and we know that for every cross section which is uz, or the displacement in z direction can be calculated as theta into psi, where psi is the warping function. We know that is a into xy. We know the value of a, and theta is also calculated. So we can write uz can be written as we know theta is t divided by pi a cube b cube into g, and we know t into a square plus b square into pi a cube b cube by g, into we know that a is b square minus a square divided by b square plus a square into, and psi is a into xy. So this can be written like this, and cancelling out these terms, we will get uz can be written as t into b square minus a square divided by pi a cube b cube into g into xy, and the contour lines giving uz is equal to constant are the hyperbolas, which can be shown So now we have the equation for uz. So if we draw the contour lines, that is along which the lines along which uz is constant, we can show the contour the lines can be, that will be in the form of a hyperbola shown like this, and here this represents the deformation in z direction or distortion due to torque in this direction, in anti-clockwise direction. And here the dotted lines represents depressed area. That means if we draw a line like this, and if we show the deformation here, it will be from we can say this as A and B, if we, and this is O. If you draw the deformation here, and the deformation will be, it was initially it was plane, and if we draw the deformation, it will be like this. At center point there is no deformation, since at center point the x and y terms are 0, and here the maximum deformation will be depression. This is in negative z direction. So here it will be depressed. These dotted line, these areas will be depressed, and solid lines represents the positive deformation. And if we draw a line like this, and here we have points A, here we have points C and D. This is A and this is B, and it can be shown that the displacement will be like at center point O there is no displacement, and there will be maximum positive displacement here in positive direction, that will be here, and here also this, at these 2 points there will be maximum positive displacements. Okay.